Hello and welcome to the first session of our workshop series, Engineering Simulation for Rhino Users by SimScale and Rhino Europe. It's great to see so many people who have joined for the first session of our workshop, which will deal with the application of fluid flow simulation. And I'm very happy that Rodrigo from McNeel Europe joined today. And yes, today we will try to show you and introduce you to the world of fluid flow simulation and show you how to combine Rhinoceros and SimScale to create accurate, high-quality fluid flow simulation to improve your product design process. Together with me is also my colleague Akram, who will answer all your questions in our question chat box, and at the end we will also have a Q&A session. Okay, but first things first, and before we start to dive into our today's journey, I would like to make sure that everybody can hear me loud and clearly and that the technical things are working properly. So guys, we are using a tool called GoToWebinar to deliver this session. And inside the GoToWebinar control panel, which every one of you now see in front of him, there is a button called Raise Your Hand. And in the case you can hear me, please click this button to show me that everything is working correctly and that everyone can hear me. Alright, I see already some hands. Seems like everything is working. However, in the case you're not feeling very comfortable to use your computer audio, or you don't have good headset or speakers, you can also use our toll-free audio service numbers to listen to the voice of the presenters. And therefore you just have to dial one of the toll-free numbers you see right now in front of you on the screen. And once you're asked, just enter the access code 192-903-379 and everything will work. Alright, perfect. So let's take a look at our today's agenda and see what we want to learn today. So as you know, this is the first of two sessions of our workshop series. The second one is next week, Monday. And today we are going to talk about fluid flow simulation. And basically this webinar is made out of three sections. So in the first part, I will explain you what fluid flow simulation basically is. We will talk about the potentials, also a little bit about the limitations, and I will introduce the cloud-based SimScale platform to you. The second part of this webinar is focusing on hands-on knowledge, and there at the beginning Rodrigo will show you how to prepare your Rhinoceros model for the simulation, and I will show you very quickly how to set up such a simulation within 5 minutes. Then we've also prepared some case studies for you where we will show you how our customers are using CFD simulations to improve their product development process. And finally, we will have time for a Q&A. So in the case you have questions, you can directly write them into our question box and we will answer on the fly. And in the case some of the questions are might relevant to the larger audience, we will discuss them during the Q&A. Alright, so let's get started. And first of all, let's talk a little bit about the fundamentals of CFD. So, and if you never heard about this term CFD, don't worry, that's exactly where we want to start. So, first of all, what is CFD? You might wonder that we mix up different terms. We use fluid flow simulation, CFD, but basically it's the same. But the difference is that not only a few people can imagine what CFD could mean. So let's dive into it. CFD stands for Computational Fluid Dynamics, which is a very scientific way to explain fluid flow simulation. And basically, CFD is a technology which allows us to perform virtual experiments on our computer for every physical phenomena where fluid flow is involved. And here on the screen you can see just a few examples of simulation which were performed with the SimScale platform. And you see that's a very high bandwidth of applications. For example, external aerodynamics. So whenever, and Formula One teams are a very good example, since they are redesigning the cars from race to race on the bi-weekly cycles. And instead of building each new design idea for a new front wing, for example, and to manufacture it and test it in a wind tunnel, majority of design ideas are virtually analyzed using CFD. The CFD simulation gives us the forces which are acting on the car, but also insights about the pressure and velocity field around the car, and can massively help to improve the aerodynamic properties of the car. But there are also other applications possible. For example, a lot of our consumers are using our CFD capabilities to simulate, for example, cooling processes inside of electronic devices. And this simulation here shows such a result. So this is basically, and I think if you really take a look at it, you can also see it. This is basically the inner domain, the inner volume of a electronic case. And here you can see the heat sink. Here are some openings, some bonnets, where the hot air can leave the system. Here are some inlet ducts, and this kind of simulation helps to predict and optimize the cooling effect of the flow. But there are also some completely different physical applications possible. For example, here you can see a simulation which is considering and modeling how the ship hull of a is interacting with the water. And basically here we are even considering two different effects. One is the fluid flow between the ship hull, the lower part of the ship hull, and the water, and the other part is the interaction between the air, the ship hull, and for sure we can also calculate waves, etc. Or, for example, here what you can see is the simulation of a heat exchanger, which is basically combining both. It's calculating the fluid flow inside the heat exchanger, but also the heat distribution inside the solid part of the heat exchanger. And these are just some impressions what you can do with CFD. And if you really want to summarize it, CFD is like a virtual lab, and it allows you to investigate products and analyze product behavior without manufacturing it. And well, now maybe one of the first questions you have is, so what is so nice about CFD? And basically I explained to you what are the capabilities of technology, but how can this help us, or how can this help every engineer, designer in the world to design better products in a shorter time and with a lower budget? So let's take a look on the left side. And this is a chart which is representing how project costs are depending on the stage of my design process. So on the x-axis you can see different stages of your product development process. So starting from the concept definition, and on the very right side basically we start to ship or build the product. And on the y-axis you can see the project cost. And now we have two curves. The first curve is showing how project costs are planned and defined. And if you think about it, it really sense. When you start to work on a new project, the very first thing you do is creating a plan, calculating budget, and related stuff. And if you think on the other hand, how in the end of the day the product development is realized, the project costs are at the beginning very low, and most of the money or resources are invested at the end of the design process. So there is basically there is a tension field between these two things, because on the one hand a lot of decision, a very fundamental decision, which are related to the cost planning are taken at the beginning, while the costs really occur very much later. And what do I want to tell you with that? Basically, if we summarize this, the most important point, or the most important fact we get out of this chart is that at the beginning of the design process, I need to take a lot of decisions, and at the beginning, these decisions are very wide. So it's like really the most important part of product development. And if you think about it, on the one hand, most of the decisions are taken at the beginning of the product development concept. On the other hand, the product is not really developed at this point, and we don't know so much about the product, and we have to do a lot of assumptions. And using CFD, or simulation in general, allows us to analyze at a very early project stage different concepts, and can help us to make better design decisions much earlier. And for sure, this kind of process can be applied on different industries. And depending on your project, it can help you to reduce the costs for design and manufacturing the product. It can help you to reduce the energy consumption of your product. It will massively help you to keep deadlines. But there's also another perspective. If you think about the role, it cannot only be used by engineers, but also by architect, designers, and a lot of other people and involved in the product development process. And since this webinar is very hands-on and is more about to show you what are the possibilities, we're not going to talk about, let's say, mathematical or physical fundamentals in detail. But from my previous experience, I know that a lot of you are very curious and want just to understand what is the fundamental idea of computational fluid dynamics and what the computer is basically doing. So let me try to explain it with a very simple example. And just imagine you want to virtually know or virtually test this airfoil design. This is an airfoil, multi-wing airfoil profile, for example, used on race cars. And if you think about CFD, you have to think about the result. So what is the result of a CFD simulation? And if we want to get a very general answer, the result of a CFD simulation is the velocity and pressure field inside our fluid domain. And now let me try to explain this in simple words. Well, there is one fact about fluid flow you should know. Basically, I can fully describe a fluid flow with the velocity and the pressure, which means if I know for every point inside this fluid domain, which is now my, let's say, virtual wind tunnel, if I know for every point inside this domain, the fluid flow velocity and the pressure of the fluid, I have completely described the flow. And there are some good and bad news. So the good news are that this is a problem where, which a lot of people worked on. And basically 200 years ago, a bunch of several scientists explored the so-called Navier-Stokes equation. And this Navier-Stokes equation is an equation which is completely describing how fluid is behaving when it's moving. And so if we take this equation and solve it, we will get the function which is for velocity and pressure. Just imagine it's a function like you know from school, and you can just put in every point you want inside this fluid domain, and you will get the velocity value for this point and the pressure value for this point. Sounds like a fair deal, right? But there's just one problem. It's not possible to solve this equation. It's such a complex equation that we will never be able to apply it on such a complex problem, and we also will be never able to solve it analytically. But there's, again, a little bit of hope, because what we can do is to apply this equation for very simple shapes and very simple systems. So, for example, if we just take this kind of element, we can apply and solve the equation. And basically, the equations are very simple. They are just expressing or stating that everything which gets inside a system will go out or stay in the system. And the consequence of this is that we can calculate the rate of, for example, mass change by calculating the difference between ingoing and outgoing mass. It's a very simple example. Just imagine you are on a party and inside the fridge are 5 bottles of beer. And now 2 people put new beer in, let's say 5 additional bottles, and 3 people will take out each of them a beer. Then in total, once this process stopped, we have 7 beer inside the system. And that's basically what we do at CFD. It's about calculating what is happening inside this element. So we cannot apply this equation on this complex model, but on simple one. So what do? We will just represent our complex problem and assemble it by a lot of small, simple elements which we can calculate. And that's basically the idea of CFD. And now we can calculate, like, instead of calculating, solving this equation analytically, we'll just get approximate results for every of these elements. And that's how CFD is basically working. And why I am telling you this? Because of two reasons, two very important things you have to consider all the time. First of all, CFD, or simulation in general, is just an assumption, and it will give us an approximate solution, not an exact solution. And the second fact, and this is very related to the first one, is that the accuracy of your simulation results depends on how you set up the simulation. If you use very small of these elements, you will get a better resolution of your simulation results, the accuracy will increase, but at the same time, the computational effort will increase. And in the end of the day, every time we're doing a simulation, it's a trade-off between accuracy and time. Well, if you're interested to learn more about the fundamentals of CFD, we have some nice and free resources on our website. And in the next couple of days, we are going to send to you an email including the recording of this webinar and the most important resources you can use to get started. Now I would like to talk with you about SimScale and what we are doing, very crispy and very quick. So, I mean, if you think about it, simulation sounds like a huge deal. However, it's not adapted by the majority of engineers and designers, and there are several reasons for this. And on the left side, you can see a chart which is showing how different technologies were adapted by industry. And if we take a look at CAD and simulation, basically both of the technologies were invented at the same time in the beginning or late 70s, and they were firstly used for military and defense and for aerospace. And as you can see, after some time, 2D CAD was a standard technology, and this was mainly introduced by reducing costs. So at the beginning, it was only available to use CAD on mainframe computers, and starting from the 80s, CAD became available for personal computers. And the same happened with 3D CAD. If you take a look at simulation, the adoption rate is still very low, and only 4 out of 100 engineers have access to simulation. And this company was founded 4 years ago as a spin-off of University Munich with the idea to change this. And if you take a look at the reasons why simulation is not adapted by the majority of companies, in the end, you will get 3 answers. First of all, the access barrier. Using simulation in the past was quite expensive, and you needed a lot of infrastructure, like you needed software licenses, special software license managers. Installing the software was not very easy. You had to update it, and also you needed a high-performance computer, it was just not like installing Rhino. It was a very complex process. The second reason is the budget reason. In the past, it was very expensive. And if you wanted to do CFD or simulation, you had to buy a computer, a very powerful, expensive computer. You had to buy the software and training. And overall, your first investment you had to do before you actually even had performed one simulation was at minimum between 20,000 to 30,000 euro, which was much too expensive for small companies. And finally, most of the traditional simulation tools are designed, let's say, for experts, for people with a know of knowledge about the theory of simulation, and they were not very user-friendly. And so we thought about it, and we found a solution. And this is SimScale, the cloud-based simulation platform. So, as I mentioned, in contrast to all other solutions, SimScale is not traditional software. It's a web app which is running 100% in the cloud, and you just need a web browser and a working internet connection to access SimScale. And then you can use it independent from your own computer, computational power. The next point is cost efficiency. SimScale is not a software product you buy, it's a software as a service. And we have a very special price model, which basically start for free. And as long as you are willing to use SimScale for non-commercial projects, and you're willing to share the simulation and results with our community, you can use it for free. And if you want to use it for professional application, you're basically just paying for what you need and what you use. And the third very big difference between SimScale and other tools it's designed for everyone. We have, as I mentioned, we have a free public plan. We have a freemium pricing model, and it's not only a web-based simulation tool, but a full simulation ecosystem. And we have also a forum and a community with more than 100,000 of engineers, which makes it very easy for people to get started. And let's just take a look on SimScale's capabilities. So first of all, we support all major disciplines of engineering simulation, including solid mechanics simulations, fluid dynamics simulation, what we are talking about, thermodynamic simulation and particle formula. And with solid mechanics simulation, you can basically simulate all the effects which are happening in assemblies when you apply mechanical load. With CFD, you can calculate all kinds of fluid flow. And with aerodynamic simulation, you can calculate and predict all phenomena where heat transfer is involved. And here we can cover both fluid heat transfer as well as solid heat transfer. And if you're interested in particle phenomena, like for example mixing and transport of bulk material, even there you can use SimScale. And for every of those, let's say, 4 physical simulation types, there are basically an unlimited number of possible applications. And you can just see 4 different applications of simulation created with our CFD solvers. So, for example, wind load prediction on a skyscraper, where you need to get to know about the forces which are acting on your building. But you can also do like a pedestrian comfort analysis of a whole city. For example, if you want to judge which is the best orientation for a new building. You can even do thermal comfort analysis in very large spaces and like calculate what are the best positions for openings for your climate control. And you can even calculate like pollution analysis. And this simulation, for example, is showing how smoke is transported in the case of a fire inside a large building. Right, and I hope you enjoyed this very first part of this webinar and that you now have a rough idea about what CFD is. And now we are going to show you how easy it is to set up such a simulation. And I'm very happy that Rodrigo joined today. Rodrigo, can you hear me?
Okay, I can hear you, Milad.
Perfect.
I was muted, so yeah, I can see your screen and hear you okay.
Yes, thank you very much for joining today. And right now, Rodrigo will show you, based on a very simple example, how to prepare such a CAD model for simulation. And yes, Rodrigo, the stage is yours. I will make you the presenter now.
Okay, thanks, Milad. Okay, so I think that you should all be seeing my screen now, right? I hope so. If not, just use the question box. Okay, great. So before we just get started, well, I'm going to assume that you guys are either Rhino users, regular users, or at least you have used Rhino briefly, so you know like the general idea. Okay, and before we just jump on Rhino itself, I would like to just briefly go through a couple of screens. Okay, the first one is this list that we have on our website, on our help pages, okay, that will describe the main, well, not the main actually, but all the file formats that we are capable of interacting. I'm just doing this because, well, I guess it's quite important to state this, because I guess that you will not be using Rhino exclusively on your workflow, okay, and the whole simulation setup and scenario. So seeing what you can import and what you can export from Rhino, okay, is probably a good idea before we get started. Okay, as you can see, the list is pretty comprehensive, and most of the formats are capable we're capable of working with them in both Windows and Mac versions of Rhino. Okay, right. Another idea that I would like to introduce before we just get started with the live demo itself, okay, is the fact that since Rhino it's not a solid modeler, okay, we will need to just take some precautions, okay, or at least clear out some ideas, okay, before we start working with the file itself. Our final aim, I guess, that is trying to get a closed polysurface, okay? That's the phrase that we use in Rhino when we describe a solid model itself, right? And that means that all the surfaces that make up the geometry should have no empty gaps between them, okay, and no naked edges, as we call them, okay? We'll see more about this later on. I'm just showing these web pages, okay, for your reference, but of course, if you have any problems with anything related to Rhino, just give us a call or send us an email, okay? So I'm just going to jump on, well, I'm working on a Windows, there you go, machine here. I usually work on Mac, but for this quick demo, I'm just going to use the Windows version, so I'm using a virtual machine here, right? So the model that we're going to work on, or that we'll be reviewing, okay, is of a high-story building like this one, okay? Right, the first thing that I would like to just point out is that this model, right now, it's made out of many different surfaces, okay? And if we just take a quick look here on the properties area, right? After we select the model itself, you will see here on the type box here that we're dealing with an open polysurface, okay? Right, this is not what we're looking for, okay? The main thing that we'll try to use fix now are any possible gaps that we might have on the file, right? The most important tool for doing this, okay, would be, sorry, here, but right here, the show edges command, right? Show edges will let you highlight any naked edges, any open edges on your file, okay? No matter if it's a polysurface, a set of surfaces, or whatever, okay? It will also let you highlight all existing edges on the polysurface, okay? But we're not really interested in these seam lines, okay? Because this just makes up the frontier, let's say the barrier between different patches of the polysurface. We're interested on the naked edges, those who define an open gap, okay? If I click on the zoom button here, Rhino will just focus and highlight these guys here. As you can see here, the gap between these two lines, between these two edges is quite small, okay? We'll try to fix this, but I think that we'll just leave that for the very last bit, okay? Since I think that in this case it will be quite easy. Another thing that you might see, or that you might realize, is that sometimes, depending on the display style that you're using, wireframe, without any shading, rendered or ghosted, you might sometimes see some artifacts, visual artifacts, and it's worth checking also the main direction of our surfaces, okay? The normal direction of surface. If you're joining together different surfaces, Rhino will just unify, let's say, this criteria, but in this case, you will see that since the polysurface is open, I still have that gap there, right? Rhino is thinking that actually the positive side of the surface is the inner side of the surface, okay? So I'm just going to flip this, there you go, to make sure that all my normals, all the positive side of the polysurface is pointing outwards. There you go. And you'll see that in this case, since I was using a separate color, okay, for my back faces, right here, okay, the color of the model has changed, okay? Right, as I was telling you, show edges, here it is. In this case, since the gap is quite small but still visible, we could create a new surface, okay, that will just cover this gap, okay? So we might do that with just a very simple 4-point surface defining the 4 edges of the gap. Okay, there you go. If I try to now select this strip that I just made, I'm going to hold Shift and click on the main building, then click on Join, okay? Apparently now I'm dealing with a closed polysurface. You will see that on the command bar. And if I select the object, there you go. Under type here, now I see closed polysurface. If you want to know more details about this element, just click on details. There you go, and you will get a full report of what's going on, how many surfaces we have, how many edges, if there are any open edges or naked edges, sorry, and so on. Okay, this one looks quite okay, but still, if you see, I mean, I want to take a quick look here at rendered, you will see that the model itself is actually quite easy, right? Even if this looks like a full single face vertical surface, okay, it's made out of many different patches. Okay, there's a command called merge all faces. Here it is, that will let you unify and merge all coplanar faces. So run it before exporting any file from Rhino, because it will let you reduce the number of surfaces in your geometry. Okay, if I go and select now, then click on details here, as I did, I think that I have 37 and now I have 17 surfaces. Okay, that's much easier, much better for me. Okay, at this point we should be able to export this as a step file, right? And before doing that, I would like to use show you another tool that will be quite helpful in these cases, clipping plane. Okay, the clipping plane will let you define a dynamic cut plane, okay, that we can use, there you go, sorry, to analyze what's going on and see if we're having a single, say, section or a single skin, better said, okay, on the file. If we have any extra wall here or any gap on the outer skin, we should be able to see it, and we can actually perform any sort of transformation on the clipping plane itself. So as you can see here, it's quite easy for us to just do any sort of live sectioning on the file. Okay, another couple of tools that will be quite useful for you guys if you are troubleshooting or trying to fix your models before exporting. The select bad objects command, here it is, the one with the skull. Okay, so what is bad object? I'm just going to go back to Mac here, and a bad object is just an object that has some sort of internal discrepancy in Rhino. Okay, that can be caused by several different reasons. Okay, they are further explained in this article, but quite often the thing you need to do with with your geometry when you identify a bad object, okay, it's first of all exploding the polysurface and trying to locate which of the 17 surfaces in this case are actually containing the error. Then you will have to individually assess what's going on, okay, and in many cases you will have to either use rebuild, reparameterize, or rebuild edges, okay, to just recreate again that offending surface, let's say, okay. But yeah, I mean, select bad objects is quite useful. There's also a command, sorry, called check objects and check all new objects that will automatically warn you whenever you create a bad object. Okay, so just right click on this icon if you want to just let Rhino let you know. I mean, Rhino let you know whenever you have a bad object. Okay, right. Another thing before we export this as a step file, right, or as any other file. Remember that in Rhino we have actually two main types of surfaces. Let's say trimmed and untrimmed. I'm just going to do a quick surface here, like, sorry, the one we have there. It's a quite simple one. There you go. If I press F10 or highlight the control points, we see that we have 4 corner points there. But actually, if I do a circle here, right, and I use the circle to trim the surface, you will see that apparently the surface is now reduced to just that single circle in there. But if I click on F10 or show the control points, there you go. I'm still seeing the main outline of the surface. Okay, that's because Rhino remembers the original elements. Okay, so again, if you want to reduce any redundant, let's say, control points that you're not using to define that particular geometry, okay, use this command here, shrink. There you go, shrink trim surface. That will let you reduce the extension, okay, of the surface to a minimum, okay? So in this case, well, I can just get rid of this circle here. In this case, I will try to run select bad objects just in case. There it goes, select bad object. Nothing gets selected, okay, that's good. I will select everything and, well, I already did that, merge all faces. That's going to unify any coplanar faces, okay. What else? Shrink, as I was telling you before, shrink trim surface. Rhino has applied shrink on all my 17 surfaces, as you can see here, and I think that at this point we should be able, or ready actually, to just export this. Yeah, one last thing, two more commands that I would like to use show you. Let's imagine I'm going to extract the lower surface. Let's imagine that I had, whoops, sorry, not copy, because I want to just fully extract this surface. Let's imagine that I do have an open pool surface like this one. There are two commands that you can use if you want to quickly fix objects with planar holes. The first one is the cap command. Cap is, sorry, here in solid. There you go, cap planar holes. It will let you automatically fix any planar holes. That is, a hole that is defined by a plane, just like, there you go, the lower one. So it's very easy if you're working with volumes and so on, right? And the other one is quite similar, but a little bit more complex. It's called create solid, okay? Create solid will do the same, but actually it will let you work with sets, let's say, of planes, and even if the outline of this plane is not completely matching the base hole that we have, okay, Rhino will be able to use, sorry, and will be able to automatically create a solid out of the intersection of these surfaces, okay? Unable to create solid, okay, I think that there must be a tiny gap, not a gap, sorry, but there you go, my volume is actually floating in space, so I'm just going to bring this down and make sure that, there you go, you can see the gap there. I'm just going to bring it down, make it line exactly on the same height. Okay, so right now I'm going to right click here for the last 20 commands that I used. Create solid, where are you? There you go, create solid, pick this one, pick all the other surfaces there, and there you go. Again, I'm going to run shrink trim surface to make sure that my lower surface doesn't get too big. Pick the object. This is a closed poly surface. And once that you're ready to export this, for instance, you can go to export selected. I'm just going to place it on my desktop, select any of the several file formats that we have, for instance, step, right? Test one, right? Click on save. And yeah, you have different flavors here, right? When exporting for different subschemes of step. And there you go. You should now be able to re-import. Actually, try to always do this whenever you're exporting anything, not just from Rhino, but from any program, okay? Try to do a round trip. Export as an external format, and then just reopen again and see if your own program is able to reopen the file, as we say, to eat its own dog food. So it should be on my desktop. There you go, test one, open. Okay, try to join all surfaces as we go, and there you go. Let me see, ghosted. It's a closed poly surface, it's a VREP, and yeah, I think that at this point probably you should be able to use go back to SimScale, and yeah, Milad, I don't know, guys, if you wanna take back over from here.
Yeah, Rodrigo, thank you very much for this impressive demo. And I think if you really stick to what Rodrigo told you, you will be able to prepare using this few commands 99% of models.
Yeah. One last thing. Yeah, no, I think that's everything because yeah, we have already mentioned these two tabs, these two help articles that will be quite useful for you guys if you are, you know, doing lots of import export and yeah, all the check options and the select bad objects command. So guys, if you want to take over, yeah, it's all yours.
Thank you very much. And yes, now let's continue our way to our first simulation. And let's just summarize what Roddy told us. So if you want to create a simulation, you have to prepare your model first of all. The reason is that models which are used for design, rendering, or even for construction are different than those kind of models we need for simulation. We have to make sure the model is watertight and is solid. And another thing, please don't use design meshes, since this is a very specific way of modeling surfaces which is not completely supported right now. However, we are working to integrate that also. But if you stick to these two tips, it will make your life very easy. And now we will set up an external aerodynamic simulation of this skyscraper design. And basically we have 3 steps. The first step is that we will import the CAD model, the Rhino model, which we have prepared before, and generate this, what I called elements. And this elements, this process of replacing your geometry with the system of small elements, it's called meshing because we're creating this kind of mesh structure. But it's a different kind of mesh than you use for modeling something. It's more a visualization of the spatial discretization. So everywhere where this mesh is fine, the accuracy is very high, and everywhere where it's coarse, it's low, because we will only calculate velocity and pressure for the centers of these elements. And once we have created the mesh, we can going to set up the simulation, which means we are telling the SimScale where the air should enter the system, where it should leave the system, and finally we can visualize the results in the web browser. And so let's get started now. Yeah, let's now switch to the web browser, and here you can see this is our homepage, simscale.com. And if you go on simscale.com, just click here and you can sign up for free and create a free community account. So, and once you have registered, you can create a new project, and here you can see a project already containing the full simulation. And the very first step is to upload the geometry, and there you can just use this upload button. And this is something quite new. Just today we released our native Rhino reader, which means that from today you don't need to use a step file or a STL file, but you can directly upload your Rhino models. Just choose a file format, give it a name, for example, building prepared, and then just choose the Rhino file and start upload. And now your CAD model is uploaded to the platform, and yes, after a few seconds you can basically start. So this is the model I imported, yes, and here you can see everything. And we can hide, for example, single surfaces. Even if we want, we can group them, and we can even scale the model and perform some other basic geometrical model operations. But now let's start to create the mesh, and I will just show you how to set it up. It's very straightforward and easy. So the first step is to create a new mesh, and the great thing is that our user interface is guiding you through all steps of the simulation. So first of all, create a new mesh, and now we have to select a base geometry which we want to use for the mesh, and we will use a building prepared, which we've just uploaded. And once this is done, you can just add a new mesh operation, and now you can choose. So we have, for example, 2 kinds of meshes. So you can use tetrahedral elements to divide your model, or you can use hexahedral elements. And tetrahedral elements, their big advantage is they can be used for both, for fluid flow simulations as well as for solid mechanic simulations, while the hex dominant mesh is only available for fluid flow simulation. But the big advantage is that this hex dominant mesh is very strong when it comes to create these meshes automatically. Usually creating this mesh takes most of the time of the simulation process. And SimScale gives you the possibility to use smart algorithms to automatically create the mesh. And basically you just have to do two things. First of all, you have to define your fluid domain, because in the end of the day we are simulating the fluid between this box and the building, and we have to define how large the space should be. We have to define like the size of our virtual wind tunnel. And we can define the size of this box by changing the minimum and maximum points. These are just two opposite points which are completely describing this cube. So let's start. Minus 350 meters in x direction, minus 350 meter in y direction, and 1.5 in that direction. This is our first point, and the other point is 350 meter, 350 meter, 350 meter. And if we now click on Save, you can see that the bounding box was updated. And basically, this is now the size of your virtual wind tunnel where you're going to calculate velocity, pressure, and all the other transport quantities of the flow. Very important that you choose the right size. If you think about it, if this box is much too small, you will get wrong results, because then you will have interaction between your model and this wall. So especially for external aerodynamic simulations, make sure to use a bounding box which is large enough. And that's basically everything. Then we just have to say which fineness level we want overall. Let's choose fine, and we have to choose if we want boundary layer elements. For those of you which are not familiar with CFD, these are special kinds of elements. These are very flat, which we use to resolve the effects which are happening at the so-called boundary layer. This will increase the accuracy of our drag prediction, especially in the near of the object. So click on OK, and finally you can choose how many computing cores you want to use to calculate your mesh. And as more cores you use, as faster it will happen. And yes, so let's start with 16.1. Click on Save, and now if we click on Start, the mesh is going to be calculated. And since this can take some time, I have just prepared a mesh with the same settings. And this is how, after approximately half an hour, the result will look like. So this is what we get. This is our fluid domain. And now, first of all, let me hide the bounding box. And now this is the shape of our building, represented by the small elements. And in the center of each of these elements, we're going to calculate pressure and velocity. And if you, for example, take a look at the floor 2, you can see that this algorithm is really smart. As I mentioned, as fine as the mesh is, as high as accuracy, and it's automatically refining the mesh in those areas where we expect to have large changes in the flow, like in the near of the object. And by the way, here you can even see this automatic but very important refinement of the edges, and it makes the mesh coarse there where we don't expect a lot of changes and where we're not basically very interested in the flow field. Right, and after we've created the mesh, we can start to set up the simulation. And again, I will show you how to do it and then show you the results, since calculating the simulation can take up to 1 to 2 hours. So we want to do a fluid dynamic simulation of an incompressible fluid. Here you can see for every simulation type some examples. And now we will, and this is, by the way, the example of our building. And now we just click on Create. And this will add a new simulation here. So this is our first simulation. It's the second. First of all, we have to choose a mesh base for our simulation. I will choose the building mesh. The next step is to choose the material we want to simulate, the kind of fluid. And basically, you can use every fluid, because you can just enter the viscosity and the density of the fluid. But for aerodynamics, we're talking about air, and let's say the most popular fluids are already in our material library, so you can just import them with one click. So we just select air, click on Save, apply it to our simulation domain. And now we basically just have to define boundary condition and describe what we want to simulate. So let's change the view to surfaces to make it a little bit more comfortable for our eyes. And I will now change the selection mode to faces and height. So here's our building. And first of all, the air is going inside the domain. So here we will define an inlet. And we just define the velocity by giving the components. And since this is normal to the x direction, and we just use 20 meters per second, so this is, for example, at a very high wind velocity. If we have an inlet, we also need an outlet where the air can leave our domain. So just use pressure outlet. Choose this phase. That's it. And what is very important, we have these two faces, the side faces. And basically, if we don't apply any boundary conditions, they will be treated as physical walls. But since these walls are not existing in reality, we can even improve the accuracy of the simulation. By the way, this is a big problem of wind tunnel testing. Besides that it's expensive and takes long, that the wind tunnels change the result. And here we can just make it a wall and a slip wall, which means that there will be no interaction between this walls and the fluid flow. Let's call it sides. And finally, we'll add for the floor and for the whole building, we will add a wall boundary condition, which is a no-slip wall, which means it's a physical wall. Well, oh, one face I forgot, for example, the one I've hidden, so this will also be a non-physical wall. Yeah, and basically that's it. Now we can save it. If we want, we can add some result control items. For example, we can calculate forces acting on every single surface of our model, or we can do scalar transport calculations, etc. And then finally, we just have to set up the simulation. So we will do 1,000 iterations. This is very important to know. CFD is based on iterative approach, which means we're not calculating the solution in one step, but calculating a solution and reuse it. So we will do 1,000 steps, and with every step our simulation results got more accurate. We will use, let's say, 16 cores, and we want a maximum runtime, let's say, of 2 hours. And yeah, click on save. That's it. Now you can just check your simulation, everything was successful, click on new, and it will be started automatically. And this can take some time. And just imagine we are now using 16 or 32 cores. If you would do it on a workstation, it would take days. And it takes around 60 minutes to run the simulation. And yes, you once the sim finished, you will get a notification. And then let's now switch to the post-processor. And I've just prepared something. I just want to show you what are the possibilities. If you want to learn how to set up the simulation step by step, we will provide you with some examples. But now let's just switch to the latest simulation step with the highest accuracy. No, and now you can see, so we have a slice here and the streamlines which are representing the velocity of the air. We can see this dead water zone and recirculation behind the building, and for sure we can create new slices, new streamlines as much as we want. So for example, if we want to change the position of the slice, we can just change the origin and make it a little bit higher. Now it moved, and we can even change what is represented. So if we're interested in the drag but not the velocity, we can take a look at the pressure, not the velocity. We can take a look at the pressure. And there are even a lot of more filters. And with the help of this, you can analyze your flow. And if there is a need and you want to do it locally, at every point of this process, you can download the results of the simulation or the mesh. Right, all right. So this was our small demo, and I hope it gave you an impression about how easy it is to set up a fluid flow simulation. And yeah, now let's use the last minutes of our workshop, and we choose a very simple example. However, we know in reality your models are more complex. And now in the last 5 minutes, I will just show you an example from one of our customers which using SimScale to improve the design of buildings. And so what's about? So for those of you who are involved in architecture or environment engineering, you might know that especially for large buildings, for skyscrapers, aerodynamic loads can be a big problem. And here on the left side, what you can see is the orange section is basically a skyscraper from the top view. And let's assume that the air is coming from the left side. And what you usually see is that around the edges of such objects, there will vortices be generated. And these vortices are very complex and changing with time. And this is very important because if you think about it, the air is applying a force on the building, and since these vortices are changing the flow field all the time, you have a lot of periodic forces which are depending on time. And let's take a look at this chart, for example. If you have static wind load, if you have a static wind load and you ramp it up, and on the other hand, like measure the forces, you would see that it's like a quadratic relation, and if you increase the wind velocity, the forces will increase. But whenever we have this transient wind loads and this complex effects of vortice shedding, it can happen that we have like peaks, and this can be very critical when it comes to design a building. And if you think about the process I described, how products or even buildings are designed, we have again a definition phase. And if you think about it, the overall building shape is defined at a very early point of your design, a project. And once you've chosen this, there is like no way of turning back. And if you find out at a very large project stage that, for example, wind loads or forces induced by wind loads are too high, then you have to invest a lot of time and resources to find a solution. And so what our customer is doing is when they're going to plan a new skyscraper, at the very first beginning, they do some very general simulations and investigate, for example, what's the best orientation for the project. And later they can use the simulation results like as boundary conditions, for example, to calculate the facet or other things. But we'll talk about this soon. So here is the simulation, some simulation. You can see like how those vortices are created at the edge. So let's take again a look. This is our skyscraper. 20 meter is the width and 20 meter and it's 150 meters high. And the wind is coming from this side, and we have this rectangular cross-section. And we have two components. We have a wind direction and a crosswind direction. And if you take a look, this is a simulation result. This is a cutting plane showing the pressure distribution at around 50 meters above the ground. And some things are obvious, like we have this high pressure field in front of the building, and he will add a large force in this direction, x direction. And we can also see this vortex. And if you take a look, on this side here, the low pressure zone is much larger on the other side, which means we will get basically two forces. We will get a force in this direction acting on the whole building and a force in this direction. And just one thing you have to really consider. Remember, force is pressure multiplied with area. Even if it's just a pressure difference of several hundred Pascal, it can result in tons of forces acting on the building. And here you can see animation. So we simulated 2 minutes of real time. And don't get it wrong. So the flow velocity on the left side direction is constant all the time, but due to this vortex shading, you can see how the flow structure is changing and how this wake and vortices are moving. And here you can see from top and here from the side. And as you know, there are a lot of different design concepts. So, for example, and you can use, and these are also introducing risks to your product. For example, you can use openings, you can have cross-section changes, or you can have soft-knit corners. And now, just as an example, I will show you the difference between this a building with soft-knit corners and the baseline model. So we did a second simulation, the same setup, basically the same model. The only difference is that we had rounded corners with a radius about 1.5 meter. And here you can see again the sharp corner case, and now we are representing the velocity, so you can see how the flow velocity is changing around this building. And now below you can also see the same simulation at the same time for round corners. And if you really take a look, you will see that for round corners, the amplitude of our vortex is much smaller. It's a much smaller vortex in general. And if we now, for example, take a look at the detail, it becomes obvious. Here we have the not soft corners. And here you can see like this big flow separation and this big vortex. And why just using this small design change, which by the way, it's my opinion, make even look better, but I think that's not the point, is massively reducing the vortex and the forces acting on the building. And here you can see like how forces are developing. So the red one shows for the sharp corner model, the pressure force acting in the side direction of our model, and here you can see that it becomes really high. I mean, we have around 1.5 million Newton, which is really high, and you know that you can even calculate or express it in kilograms, and then we are talking about 150 tons of force acting. And here you can see how this changed. Using the soft corners, we get a completely different result and completely different forces. Here you can really see like that with the sharp corners we have very strong intermittent forces with high peaks, which is a problem because in the end of the day, if we have this load case, our design have to work even for the largest peak of the force. While using this sharp rounded corners, we get much smaller forces, 3 times smaller, but it's periodic, which is, by the way, also very good because it's not like changing all the time. And this kind of simulation help our customers massively to improve the product development quality, and maybe the most important thing is that this was a technology which was not able to them before using SimScale because of the high cost and high effort of using on-premise solutions. Okay, great. Thank you very much. And now we have just a final slide showing where everywhere you can apply CFD when you are designing buildings. So at the very beginning, you can really experiment different, let's say, main shapes for the building, different orientations, and especially what you can see here, for example, if you want to build an skyscraper in an existing city where you have other buildings, the interaction with the surrounding can be very important. And these are things you can very easily simulate. And you even don't need to have the detailed model because you can just make a rough model of some cubes for the very first preliminary analysis. And just kind of analysis can help to avoid massive wrong decisions. But even in later points we can use it. For example, when we already know our overall shape and the overall design of the building, we can start to, like, for example, investigate different facet designs. And at the later point, when we basically finish the design, we can use the wind loads calculated from the simulation as input for structural analysis. Here you can just see a lot of different examples where SimScale was used. And finally, one very important question. A lot of people ask us, "Oh man, what's about our accuracy?" They say, "Well, it's a nice tool, but how can I be sure I can trust the results?" And SimScale is using leading scientific codes in the background, also used by large companies like SLRush, Volkswagen, Airbus, and even by the Norman Foster Group. But these tools were not accessible before, and so let's just take a look. And this is a typical validation case. So on the left side, you can see the data, which was created during a scientific research study. And basically, what they did is they took a very simple model for a building with a defined inlet velocity profile, and then they measured the velocity profile, the velocity distribution here in the near of this edge at 3 positions. And right, you can see in blue the experimental results, and in red the results using SimScale. And this is just the velocity profile, so this is even not the final result. And this is, by the way, the most difficult part to model, what is happening in the near of the wall. And here you can see really it's very close. And we're talking about accuracy, which is really high. And if you're interested in the accuracy, we have a lot of validation cases you can access on simscale.com and just look for support and documentation. All right, and now I think we have a lot of questions. We basically even prepared a second demo, but we're running out of time. Just to give you very quickly another idea that how you can also use SimScale and CFD for architecture. For example, if you are going to do interior design and plan the internal part of a building, especially when it comes to heating and ventilation, you can simulate like temperature distribution. And even what is very nice, here you can see that's 2 different designs, 2 different concepts, and like then how the different designs perform. And here you can, for example, see that the temperature distribution is might better using the new design. We have a much more uniform cooling air distribution. If you take a look at the temperature distribution, it's the same. Here you can see this basically it was a room for servers. It was an IT room, and what you want is to get the heat get the heat out of or away from the racks. Here you can see, like, using this new design, you get much cooler air around the racks. And total, just with this small design study, at the very first attempt, our customer was able to reduce the average rack temperature by more than 10%. And again, we did validation here, and again you can see the accuracy of our results. And just wrapping it up, because this is very interesting, so for creating this simulation, which massively helped our customer to improve his product and reduce the development time, he had just to spend only 2 hours of manual time, including geometry preparation, meshing, upload, 4 hours of computing time, 7 hours of computing time, so it took 7 hours to calculate the simulation, around 400 core hours. Great, and yes, we're a little bit over time, so now let's use the rest of the time for the Q&A. And I can imagine we have a lot of questions. So let's just start, and whenever you have a question, just write it. Okay, it seems like my colleagues answered, or Akram answered most of the questions during the webinar. If you now have a question with one answer, please write it now into the question box. And in the case you have some, you watch this session as a recording, you can also reach out to our sales team for every question you have, or use our forum. Right, okay, seems like all questions were answered. Some people like if we can, some questions are coming up. So let's start. Just 1 second. Just 1 second. Okay, so The first question was by Jose Varela, and he wants to know if it's possible to download the results of the simulation to the computer. And yes, for sure, this is possible. You can basically use every post-processing software you want, and we are offering different file formats you can choose to download the results. Then the next question is Jose also, that he's involved in marine engineering, and he wants to know if we have some examples with fluid flow waters and boats. And yes, for sure we have such examples, and the easiest way to check out the examples on your own is to go on simscale.com, and you even don't need to have an account for this. Just go on public projects, and now you can see all public simulation projects. And for example, here the first thing I find on the first page is a 6 degree of freedom floating simulation of a ship hull. Okay, then Sebastian wants to know if it's possible to get some manuals for of CFD for vessel design. And we are offering in general a lot of documentations and tutorials for a very large bandwidth of applications. And the best here is really to check out on our website our learning resources. And we have the SimWiki, where you will find for a lot of examples, and we also have some other workshops focusing on applications. For example, we had the biomedical workshop last year. You find the recordings on simscale.com webinars and workshops, and they will also show how to set up a vessel simulation. A lot of people ask whether they can sign up for an account. Just go on simscale.com and let me mark it. So just simscale.com and then just click here. I can show you how it's working. Let me log out, go back on simscale.com, maybe I delete, and then you can just click on sign up for free, enter your name, email address, phone number, and then you go. No hassle, no credit cards, very easy. Okay, let's see. Claudio wants to know if we have hydrodynamic models for waves through an inlet, and that's also a very good point about SimScale cloud-powered software. Unfortunately, we have it available right now, but we get similar requests from some customers and users several weeks ago, and right now we are developing it, and in the next couple of weeks we will release. And that's a great thing, by the way, about cloud-based software. You don't need to update it, and we can very quick adapt new features and feature requests from our users. Right, okay. I think the other questions were answered. There are some questions regarding the ship hull design. So let's again take a look at this project. So yeah, then it's you just, for example, here, what is considered is the boat as a rigid body, and we can really calculate for this boat simulation like the hydrodynamics and aerodynamics of the boat. Then Florian Rist wants to know if we can give any idea about the pricing. Yes, for sure we can. So let's go back on the SimScale page. And the good news is, basically, SimScale is free. So let's go on pricing. And we have basically two kinds of plans. The first plan is a community plan, which is completely for free and gives you 3,000 call hours and more on request. And the only difference between our free community plan and the professional plans is the fact that all projects created with a community plan are public available and become part of our public project library. And this will help other users to get started. And for sure, when you're doing professional work, you don't want to share your stuff, you can use a professional subscription. And since everyone has different requirements and needs, we stopped using a fixed price model, and the price is custom, but we're talking about starting from, let's say, 2,000 euro, and most of our customers are somewhere between this, 2,000 to 5,000 euro. Then George wants to know if there is a sample for fume hoods. Yes, I can remember that there is an example because I did it myself. Let's see if we can find it. But guys, really, the easiest thing is just to check it out yourself. Our project library. All right. So, for example, let's take a look for hood, for example. And here, for example, is an inlet duct and hood. Here is, I think, what you looked for, right? Such a suction nozzle. Okay, great. It seems like really most of the questions were answered. And if you have questions regarding the details of the pricing, just reach out to my colleagues from sales, and they will give you an individual offer based on your needs and your budget. But let's say usually our customers usually the price is not related so much to the core hours. So it's, as a professional customer, it's quite cheap to buy new core hours. But the price, and that's the reason why we can't give you a fixed price, is based on the number of core hours you want to use. Okay, then, yeah, if you got another question, if you're watching the recording and weren't able to ask live question, you can also reach out to us using email, and my colleagues and I will be happy to answer all of your questions. All right, okay. If there are no further questions, I would like to say thank you very much. And okay, one last question by Claudio. He wants to know what's about the movement of the ship, since it's allowed to trim and sink, and if the hull mesh dynamically is remeshed. No, Claudio, that's not necessary, because in this case we are running a multi-phase simulation. So we are like considering this moving of the boat a different way. But if you have questions related to detailed application, please contact my colleagues, and we have specialists like for every different industry. Thank you very much for joining. I hope you liked it, and don't forget, Monday we have the next session about finite element analyzers. Have a nice weekend. Thank you very much to our guest speakers, to Rodrigo and to Akram for managing the chat. See you soon. Bye.